In this video, we'll explore Word2Vec, one of the most popular word embedding techniques. Word2Vec uses two main architectures to generate word embeddings: continuous bag of words, CBOW and Skip-Gram. This video was produced in Korean, then translated into English. The audio was generated by AI, text-to-speech. In this chapter, we will look at Word2Vec. First, we'll briefly review the papers that introduced the CBOW and Skip-Gram models. Then we'll take a look at the model architectures. Next, let's implement simple Word2Vec models in Keras. To simplify the problem here, we use standard softmax for the output layer of the model. The authors of this paper used hierarchical softmax to reduce the computational time required to train models on huge data sets. In the following videos, we'll take a closer look at Huffman trees and hierarchical softmax, and implement a tiny Skip-Gram model using hierarchical softmax in TensorFlow. Word2Vec was presented in the paper entitled Efficient Estimation of Word Representations in Vector Space by Tomas Mikolov et al. In 2013. They proposed two novel model architectures for computing continuous vector representations of words from very large data sets. In the same year, Tomas Mikolov et al. Presented several extensions in this paper that improve both the quality of the vectors and the training speed. The key points of these papers are as follows. Let's go through these one by one in the next slides. We'll look at the last two in the later videos. The first key point is a neural network-based distributed representation for words. In natural language processing, words can be represented using various techniques, broadly categorized into traditional local representations such as one-hot encoding and modern distributed representations such as Word2Vec. In a local representation, each word is represented by a single dedicated unit, a single neuron. Only that one unit is active when the word is present. In contrast, in a distributed representation, each word is represented by a pattern of activation across multiple units. And each individual unit participates in the representation of multiple different words. Distributed representation, which represents words as continuous vectors, has a long history. A very popular model architecture for estimating neural network language model, NNLM, was proposed by Bengio et al. In 2003, as discussed in the previous video. This model has been followed by many others. Word2Vec is also a neural network-based distributed representation model. The second key point is to train a simple model on huge data set. The NPLM, which we looked at in the previous video, consists of input, projection, hidden, and output layers. This is the input layer, and this is the projection layer, which is a linear layer without an activation function. This is the nonlinear hidden layer, and this is the softmax output layer. This architecture becomes complex for computation between the projection and the hidden layer, as well as the softmax computation. The authors of this paper proposed two simple architectures that do not have hidden layers and introduced techniques that can be used for learning high-quality word vectors from huge datasets with billions of words and with millions of words in the vocabulary. The next key point is hierarchical softmax, which is a computationally efficient approximation of the full softmax. In the context of neural network language models, it was first introduced by Morin and Bengio in their 2005 paper, Hierarchical Probabilistic Neural Network Language Model. The softmax function incurs a significant computational cost in neural networks with a large vocabulary, because its computation time is directly proportional to the size of the vocabulary, often becoming the primary performance bottleneck. One way to solve this problem is to use hierarchical softmax. In this paper, Tomas Mikolov et al. Used hierarchical softmax, where the vocabulary is represented as a Huffman binary tree. A Huffman tree is constructed based on the frequencies of words in a corpus. More frequent words are assigned shorter paths in the tree, leading to more efficient computation of word embeddings. Instead of a single large softmax computation, hierarchical softmax computes sigmoid as it traverses a path from the root node to a leaf node, a predicted word, in the Huffman tree. This reduces the computational complexity from being linear in the vocabulary size to being logarithmic. We'll go into more detail about this in later videos. The next key point is parallel training of neural networks. To train models on huge data sets, the authors implemented several models on top of a large-scale distributed framework called disbelief. This allows us to run multiple replicas of the same model in parallel, and each replica synchronizes its gradient updates through a centralized server that keeps all the parameters. They used mini-batch asynchronous gradient descent with an adaptive learning rate procedure called AdaGrad. Under this framework, it is common to use 100 or more model replicas, each using many CPU cores at different machines in a data center. For more details, please refer to this paper. The next key point is the concept of multiple degrees of similarity. The term multiple degrees of similarity is a concept used in natural language processing, particularly in the context of word embeddings and Word2Vec models. It means that words can be similar to each other in several distinct ways or dimensions simultaneously. This similarity can be both semantic and syntactic. For example, king and queen are related to royalty and are semantically similar. The same goes for the relationship between man and woman. Semantically similar words tend to be located close to each other in the word embedding vector space. And kings have similar endings and are syntactically or grammatically related. Somewhat surprisingly, it was found that similarity of word representations goes beyond simple syntactic regularities. Using a word offset technique, where simple algebraic operations are performed on the word vectors, it was shown, for example, that vector king minus vector man plus vector woman results in a vector that is closest to the vector representation of the word queen. Figure 2 of this paper shows the two-dimensional PCA projection of the 1,000-dimensional Skip-Gram vectors of countries and their capital cities as follows. The figure illustrates ability of the model to automatically organize concepts and learn implicitly the relationships between them, even though no supervised learning information about what a capital city means is provided during training. Next, let's look at the Continuous Bag of Words model, CBOW. The model presented in the paper is as follows. It consists of input, projection, and output layers. This can be expressed in a more understandable way as follows. Before looking at the structure of the model, let's first take a look at the dataset. Let's say we have a tiny corpus with only 5 sentences, like this. We create the vocabulary from this corpus as follows. Then generate a training dataset as follows. We used 5 grams in this example. This is the target word W2. These are the previous 2 words WT-2 and WT-1. These are the next 2 words WT+1 and WT+2. CBOW predicts the current word WT based on the context of surrounding words. We generate the training data in this way. If we convert the words to their corresponding indices in the vocabulary, it would look like this. These are the input vectors that will be fed into the model, and these are the targets, i.e. desired outputs from the model. This vector is input into the CBOW model. As we saw in the previous video, the embedding layer selects a word vector corresponding to each word from the matrix C. This is the table lookup in C process. And then it adds all these word vectors or calculate the average. This is a latent vector for the input context words. This is fed into a hierarchical softmax or standard softmax output layer. Each neuron in the output layer outputs the conditional probability for every word in the vocabulary given the context words. When the first data point is input to this model, neuron 4 outputs this conditional probability. We want to maximize this probability. During training, we update each word vector via backpropagation to maximize this probability. After training, we get a word vector for each word in our vocabulary. The final goal of this model is to find an appropriate matrix C. Next, let's take a look at the continuous skip-gram model. The model presented in the paper is as follows. Like the CBOW model, this also consists of input, projection, and output layers. This can be expressed in a more understandable way as follows. In skip-gram, the center word or current word becomes the input of the model, and the surrounding context words become the output of the model. It predicts the surrounding context words given a single target, center, word. This model has multiple output layers to output context words. When a data point is input to this model, each output layer outputs the conditional probability for every word in the vocabulary, with the context word having the highest probability. Update this word vector via backpropagation so that these probabilities are maximized. The final goal of this model is also to obtain an appropriate matrix C. Skip-Gram can be configured as a model with a single output layer like this. Generating training data with a single context word makes the Skip-Gram model simple, like this. The performance of this model is identical to that of the model in the previous slide. In this video, we looked at the structure of the CBOW and Skip-Gram models. In the next video, we will implement the models using Keras.